All right, welcome everybody. I want to use total unimodularity to prove König's theorem. König's theorem says that in a bipartite graph, the number of edges in a maximum matching is equal to the number of vertices in a minimum vertex cover. Why is total unimodularity going to be relevant? Well, it's going to boil down to this lemma, which says that the incidence matrix of a bipartite graph G is totally unimodular. You know, in a bipartite graph, the vertex set can be split into two components, X and Y. So some of the vertices are in X, the remainder are in Y, and no edge, or I'll say this as every edge connects one vertex in X to one vertex in Y. What is the incidence matrix of a graph? Well, you list all of the edges as columns, and you list all of the vertices as rows. And then I'll fill this in by looking at the columns. In each column, I put a 1 for the incident vertices. So E1 has incident vertices V1 and V4. E2 has incident vertices E2 and E4. Edge E3 is connected to vertices V3 and V4. Edge E4 connects vertices V2 and V5. And edge E5 connects vertices V3 and V5. And then all of the other entries are 0. So you'll notice that every column corresponds to an edge. And so every column has exactly 2 1s because an edge connects 2 vertices. All right, so take any bipartite graph, consider this incident matrix, vertices, edges, and we claim that the matrix is always totally unimodular, meaning if you take a square submatrix, L by L square submatrix for any, for L equals 1, 2, 3, then that submatrix has to have determinant 0 or plus or minus 1. We'll prove this by induction on L, the size of your square submatrix. Okay, so let's start with our base case, L equals 1. We're looking at 1 by 1 submatrices, things that just look like that. These are all totally unimodular because all the entries of our matrix are 0 or 1. This is clear by the definition of incidence matrix. To be totally unimodular, every entry has to be 1, 0, or -1. Here, we're looking at unsigned incidence matrices, so every entry is 0 or 1. Okay, so now the beauty of induction, we can just go ahead and assume that every submatrix of size L-1 by L-1 has determinant -1, 0, or 1. And now we need to prove that it's true for a submatrix of size L by L, and then we're done. So let Q be an arbitrary L by L submatrix. If any column of Q is all 0, then the determinant is 0. Let me draw a picture of that. So what if I cut out those so that here's my remaining square matrix Q. I have a column of all zeros, and so clearly the determinant is 0. If any column of Q has a single 1, then we know that the determinant is 1, 0, or -1 by induction. So let's do an example like that. Okay. Look at this remaining 3 by 3 matrix Q. Here's a column that has a single 1. And when I do cofactor along that column, I just get 1 or -1 times the determinant of this square matrix, which is smaller. So by induction, it has determinant 1, -1, or 0. So what's the only remaining case? If no column is all zeros, if no column has just a single one, then every column of Q has 2 ones. Right? So no column is all zeros, no column has a single one. So we've cut things out in a way so that all of the remaining columns, the part that remains, we have 2 ones that still remain in each column. Let me do a picture like that. So here, if I cut just that out, then the 4x4 matrix that remains, oh no, that's not right. Let's cut this out. So the 4x4 matrix that remains in the bottom right, every column has 2 ones in it. Okay. And I need to show that this matrix still has determinant 1, 0, or -1. I'll prove that this remaining matrix always has determinant 0, actually. Okay. So let's look at the vertices in X. So of my remaining matrix, the vertices that are in X are V2 and V3. Okay. V1 is also in X, but I've removed it. I've removed that row. When I add those 2 rows together, I get the vector of all ones. Okay. So when I add those 2 rows together, I get this vector of all ones. And the reason is because every edge connects one vertex in X to one vertex in Y. Okay. So my columns all had 2 ones in them, and one of those ones corresponds to a vertex in X, and the other one corresponds to a vertex in Y. So yeah, of the 2 edges in each column, you know, one of them corresponds to a vertex in X, and yeah. Okay, same thing if I look at the vertices corresponding to Y. So look at the vertices corresponding to Y, V4 and V5. If I sum over those 2 rows, I also get the vector of all ones. And that's because every column also has a 1 that must connect to a vertex in Y, just because every edge goes from X to Y. So I found disjoint rows that both sum to the same vector. That means that my rows are linearly dependent, right? I could take a non-trivial linear combination of the rows and get the 0 vector. And since my rows are linearly dependent, therefore the determinant of the square matrix is 0. Questions? It's sort of a cool proof using the properties of bipartite graphs.
I have a quick question.
Yeah.
When we're summing up all rows for vertices in X, is that all rows for vertices in X that are also in Q?
Yeah. Yeah. But, you know, we haven't noticed that we didn't remove any ones from any of the columns, right? Like when we cut off this vector V1, we didn't remove any ones because the columns that remain, you know, still have all of their ones in the square submatrix.
Wouldn't we always be in the third case? Or no. Okay, this is all columns of Q, not all columns of the big matrix. Sorry.
Yeah, no, definitely. Right. Yeah, you'll remember like our first examples, you know, if you cut out you know, enough stuff, I could get a column, you know, that's all zeros. The rightmost column is all zeros. Yeah. Other questions? Okay, so the key takeaway is that in a bipartite graph, its incident matrix is totally unimodular. We now have a very nice proof of König's theorem. König's theorem says that in a bipartite graph, the size of a minimum vertex cover equals the size of a maximum matching. I've drawn a maximum matching on the right. So in a maximum matching, you try to include as many edges as possible. I've included all the ones in blue, subject to the constraint that every vertex can only be connected to one edge in your matching. Okay, so I couldn't, for example, add in this red edge because then vertex E would be connected to more than one edge. So in this matching, I have 6 edges. And it turns out that's the best you can do. What is a minimum vertex cover? A minimum vertex cover is you want to use as few vertices as possible so that every edge is connected to at least one of the vertices in your set. So here's a cover by 6 vertices. And you can see it's a cover because let's just go in and sort of rule out all the edges. So Q covers these edges. V is in my set, it covers these edges. C is in my set, it covers these edges. D is in my set, it furthermore covers these edges. E is in my set, whoops, and it covers these edges. And G is in my set, and it covers these edges. Okay, all of the edges got covered. That was sort of pretty picture. And the point of König's theorem is that even though we're talking about quite different things, vertices versus edges, for any bipartite graph, this maximum or minimum number is going to be the same. 6 edges is the best you can do in a matching, or 6 vertices is the fewest vertices you can find in a cover. All right, so it's time to prove this. We're going to let A be the incidence matrix of this bipartite graph. So you know, what does A look like? A looks something like I have all the vertices as rows. So A, B, all the way up to G, and then Q, RS, all the way up to W. And then I have the edges along the columns, E1, dot, 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 all the way up to E, S. Okay, and then all of the entries are 0s and 1s, and you'll remember I have exactly 2 1s in every column. This matrix is totally unimodular, and we'll use that to our advantage. We're going to write down linear programming problems that a priori are integer linear programming problems that solve these 2 problems, the maximum matching and the minimum cover. Let's start with the maximum matching. Okay, so each edge is going to have a label. It's going to be 1 or 0, turns out. And 1 is going to be if it's included, and 0 is going to be if it's not included, like this edge. Okay, so this constraint, AX is at most the vector of all 1s, is saying that each vertex is incident to at most 1 edge. Because I have this X vector telling me which edges I'm including, and then I multiply it by my matrix A, multiply it by the row corresponding to a particular vertex. And to get at most 1 in that row means that my set of edges is incident to that vertex, only one of those edges is incident to that vertex, or at most one of those edges is incident to that vertex. Do you see that? You know, the vertex row has ones corresponding to all of the edges that are connected to it, but then I take my vector encoding which edges I have, and I better get at most one, otherwise I don't have a matching because I would have, you know, too many edges incident to a vertex. All right. We just need to add in this integrality constraint, and then it turns out that together, the integrality constraint and this constraint implies that furthermore, each xj can't just be an arbitrary integer. It has to be either 0 or 1. All right, so solving this problem solves the maximal matching. It's not an easy problem to solve a priori because of this integrality constraint. We'll use the total unimodularity of A to just get rid of that, right? We can get the same optimum with an integer solution as you can with an arbitrary solution by the main theorem of total unimodularity. Okay, the problem on the left solves the minimum vertex cover problem. Each yi is a variable associated to a vertex. It's 1 if your vertex is in the cover, and it's 0 if your vertex is not. A transpose y being at least 1 tells us that every edge has to be adjacent to at least one of the vertices in our cover. And the reason for that is, you know, y is this vector of which vertices are included. And then when I take A transpose, you know, now my rows correspond to edges, right? And then I have to say, okay, this edge, I know which vertices it's incident to. Is it incident to at least one of the vertices in my cover? It better be, otherwise it's not a cover. All right, we add in this integrality constraint. So, you know, a vertex will have a label that's, you know, 0, 1, -1, 2, -2. The labels can't be negative by this constraint. A priori, you could label a vertex with the label 2, but in any optimal solution, you'll never need a label 2. You could do better just by using a label 1. A label 1 would suffice whenever you had a label 2, because you only need to get up to at least the value 1. And labeling 1 is always going to minimize things better than labeling a vertex 2. So sure, you could have a feasible solution where you label a vertex with 2, but an optimal solution, minimizing the sum of vertex labels, is always going to have labels 0 and 1. Okay. And the vertices labeled 1 are the ones we include. So matrix A is totally unimodular, which means you can just cut out this integrality constraint and you don't change the optimum value, right? Because once I've removed this integrality constraint, I now have a truly linear programming problem, and the total unimodularity theorem said I could find just as good of an optimal solution with integer constraints. And A being totally unimodular tells us that A transpose is totally unimodular. And so same thing here. I can get the same optimum even if I remove that constraint by the main theorem of totally unimodular matrices. So now these are two truly linear programming problems. And furthermore, they're dual to each other, right? So I had this max got changed to a min. You know, I had n variables and m constraints, and now I go to m variables and n constraints. My matrix A got transposed. I think this less than or equal to turned into this greater than or equal to, and this greater than or equal to turned into this greater than or equal to. So the values of these two linear programming problems are equal by the duality of linear programming. we couldn't apply duality until we got rid of these integrality constraints, because we don't have a duality theorem in full generality for integer linear programming. But once we got rid of these integrality constraints using total unimodularity without changing the values of the optima, then we can just apply the duality of linear programming to see that the maximum and the minimum for these two are going to coincide. In this particular example, the maximum is going to be, of course, 6, and the minimum will also be 6. All right, so I thought this was a really cool connection, a pretty nice mathematical concept, total unimodularity, that's relating to this combinatorial problem of matchings and covers via the duality of linear programming. What questions do you have? If none, thanks so much.